Hello everybody. I welcome you all to NCAS geology class. Today I will discuss about isostasy, and the points that I will deal are the derivation of naming of isostasy, surface irregularity and Dalton's view, definition of isostasy, experiment observations which are made to explain isostasy, theories proposed by Airy, Pratt and Heiskanen, how isostatic balance is offset, then evidences of isostatic adjustment. So about these points I will discuss what is isostasy. So let us start. How the term isostasy came into being, let us know. The term isostasy has been derived from the Greek word isostasios, that means in equipoise or in balance. Iso means equal, stasis means standing. Hence, isostasy means equal standing. That is, all the crustal blocks are standing over the substratum with the balance. We see that all the vertical irregularities or the relief features of the earth crust, they are well balanced over the substratum. The fold mountains, the hills, valleys, ocean basins, continents, they all are found to be balanced over the substratum. So this balance is referred to isostasy. This theory was developed from the gravity survey made in the mountainous region of India during 1950. The term isostasy was first used by the American geologist Clarence Dalton in 1889. So what is Dalton's view? Earth's surface is uneven. It presents mountains, hills, plateaus, valleys, plains, peneplains and ocean basins. Compared to the size of the earth, these uneven features are negligible and they are all in perfect balance. It is known that earth came into existence in form of a gaseous or liquid body. Any body that is made up of gaseous, liquid or plastic material, if rotates with respect to an axis, assumes a spherical shape. So similarly, earth has assumed spherical shape, but the unevenness of the surface features of earth do exist. The surface is not smooth. We have the vertical irregularities over the earth crust, which are called as the relief features. According to Dalton, irregularity exists due to the presence of materials of different density. Elevated masses are characterized by rocks of low density because they bulge during the rotation due to their less density, and the depressed basins are represented by the rocks of higher density because denser body sinks. So there must be a level within the earth where pressure due to the elevated mass and the depressed areas would be equal. This is called isopistic level or level of uniform pressure. Below it there is asthenosphere. So asthenosphere is defining the isopistic level over which the standing blocks of earth are all balanced. This fact was proposed by Dalton. Let us define isostasy. Thus, isostasy is defined as the equilibrium in the vertical distribution of different blocks of Earth's crust. It is the perfect balance of all the vertical irregular features. Or simply speaking, it is the balance in arrangement of different blocks of Earth crust. If there will be loading of mass in one block, it will sink, making provision for adjacent block to rise so that perfect balance can be maintained. So, rise and subsidence of Earth's blocks are going on to maintain the balance over the asthenosphere, which defines the isopestic level or level of equal pressure. Many experiments were made to explain this theory of isostasy. Let us discuss. Ice floats on water. It rises by 1/10 of its volume with 9/10 parts below water. If the upper 1/10 part of the ice is removed, 1/10 of remaining ice rises above water. Similarly, crustal blocks rise on unloading of pressure caused by erosion, melting of ice sheets, or by gravity transfer or faulting. Consequently, there occurs loading and sinking of adjacent crustal blocks. We know that the mountainous regions are clad with glaciers. During winter season, heavy growth of glaciers takes place. They exert pressure over the underlying rocks. So, pressure builds up below the mountainous region. And during the days of summer, ice melts. The glaciers melt. So, the pressure is released. And the water derived from the melting of ice, they are brought to the rivers. So, this is a type of unloading of pressure. Because of this unloading, it is thought that the hill masses, they start rising. So, with the pressure, the earth blocks face sinking, and with unloading of pressure, the earth blocks face rise. As a result of which, a perfect balance is maintained for all the crustal blocks over the earth. So, see, this ice experiment is one that clearly proves that the earth blocks are subject to rise and fall. Then the survey of value of G on different locations of earth have given information about distribution of mass vertically and horizontally. Sir George Everest, a surveyor general of India, studied the value of G at two places south of the Himalayas, that is at Kalyana and Kalyanpur. Kalyana is nearer the Himalayas. Kalyanpur is little away from Kalyana and hence farthest from the Himalayas. At Kalyana, the pendulum bob is found to be inclined, being pulled by the Himalayas. But at Kalyanpur, it is vertical because the pull of the hill mass Himalayas is not there. So, as per the law of gravity, every matter in the universe attracts every other matter with a force which is directly proportional to the square of the masses and inversely proportional to the directly proportional to the product of the masses and inversely proportional to the square of the distance between them. This theory plays a role here because of the presence of the Himalayas. The pendulum bob is attracted towards it, and at Kalyanpur, which is farthest from the Himalayas, there the pendulum is not found to be affected by this pull, and that's why it shows vertical orientation, or vertically it is found to swing. It is found to stay vertically downwards, whereas near Kalyana, the pendulum bob is found to be attracted, bit bent from the vertical towards the Himalayas. This proves the law of gravitation. So here we see that this is the swinging pendulum. It is observed to be here, but it is expected to be here, but it is observed to be here. Little closer to the vertical. It is why? It is because of the pull of the Himalayas. But we know this observed difference in the swinging of the pendulum is seen because the Himalayas is balanced by its root. If it is exposed by 110, this will be 910. So it has a root, and this root exert the pressure over the pendulum, because of which the expected deflection is not found to be present. It is somewhere between the vertical and the expected deflection. It is the observed deflection. It is because this underlying root that causes the pull. That has been tested. So the expected swing is more than observed swing. It is less because of this root, because of the root of the Himalayas. So the law of gravitation states that every matter in the universe attracts every other matter with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. F is equal to G m1 m2 by r square. Hence, if we think that Himalayas is rootless and is made up of material as seen outside, its pull will be more on the bob of the pendulum, so that it will swing more towards the Himalayas. That will be the expected swing. This would have been the expected swing. If we think that Himalaya is rootless, it is not having rootless. Whatever is exposed, that exerts the pull. So pull will be more. But actual swing is found to be less than the expected swing. It is due to compensation by the root of the Himalayas. Its root is about 9 times the height. Observed value of G proved that Himalayas have thick root, due to which it stands well. It exerts a pull over the pendulum bob so that it does not swing to the expected level. It is somewhere between the vertical and the expected deflection point. So, because of this route, the Himalayas stands very well. Similarly, if you take other example, granite is 10% lighter than the basalt, so it has higher volume and appears as raised continental crust. Basalts are dense, their volume is less compared to the granite, hence they appear as depressed ocean basins. For equilibrium, equal mass must occur underneath equal surface area. This fact you have to remember. For equilibrium, equal mass must occur underneath equal surface area. Therefore, continents appear higher compared to the ocean basins. So these are some of the evidences that account for the fact that the high standing masses, they have their root, they have their substratum. Higher the mass, higher the root, that root of the same mass that goes inside into the earth, so that the high standing body stands perfectly over the earth. Now let us come to different theories which have been proposed to explain the theory of isostasy. There are three common theories: Airy's hypothesis, Pratt's hypothesis, and Hayes-Cannon's hypothesis. Let us discuss Airy's hypothesis. According to Airy, continental crust is of uniform composition, so he thought that rock masses of uniform density float on substratum of higher density. It is similar to floating of icebergs in water. As a small iceberg sinks to small depths by big iceberg and big icebergs sink to the deeper depth, similarly smaller crustal blocks sink to small depth and bigger crustal blocks sink to the greater depth in the substratum. So there is no definite level. So there is no definite level in the earth where these are balanced. If we take into account Airy hypothesis, according to Airy, the crust has uniform density, one density, mu c. And here it shows the highlands or fold mountains, or let us say Himalayas. It is standing high over the ground and it has its root. This is the root. And so this is the crustal block. So the pressure that is found here is equal to pressure that is found here and is equal to pressure found here. Here it is the ocean filled with water, and ocean is thin, oceanic lithosphere is thin, continental lithosphere is thick, and the continents below the fold mountains are very thick, as we find in Himalayas. So the pressure here is equal to the pressure here, and the same is equal to the pressure below the oceans. And according to Airy, these crustal blocks, they have same density. Let us say rho c. This is rho c, crustal density, and below it we have the mantle having density rho m, and this is Ta, this is A, this is R. R is the root, A is the anti-root, H is the mountain height, Z is the basin depth, this is the basin depth, rho C is the density of the crust, rho M is the density of mantle, rho W is the density of water, Ta is the depth of compensation below the root of the continental masses, Ta is the normal thickness of the crust. So, by taking these into account, we see that pressure is rho Hg, G acceleration due to gravity, H is the height, rho is the density. So, the density of this portion is given by this. Density of this block is given by this. So, if we rho G, rho GH, rho GH, rho GH, so these two they have been compared by this equation, which gives a root to be found out by this formula. And A, this anti-root, is found out to be by this formula, which is this is found out when you compare this one with this one. It is actually the study of the pressure H rho G. So here the pressure is this block H rho C, then this block Ta rho C, then this block R rho C, then this is the level of compensation, then this block dA rho m. So this gives the total pressure of this block. Then let us come to, this is the continental side, Ta rho C, this is the pressure of this block. Then the pressure of this block is R rho m. Then this depth is dA rho m. So this gives the pressure of this block. So they are equal. So they have been balanced and R is found out to be here. And when this is compared to this one, we get A anti-root to be given by this formula. So here he thought that all the crustal blocks are having same density, and these crustal blocks, they sink to different depth depending upon their density. Higher the height of the crustal body, deeper will be its root. So this is the root in case of the pole mountains, and this is the root of the normal crustal blocks, and here it is the oceanic basin, ocean, and it is big because it is thick, that's why it is thin, and up to here the mantle is there. So all the crustal blocks, they present same density, but they go to different depth depending upon their height. More the height, more the depth the mass goes, so that the balance is being maintained. In case of oceans, because it is denser, the ocean basins, they are deep, they are having small depth, that's why the root is small. They have their anti-root. It is the pole mountain, it has its root. This is the root, this depth it goes. So in this manner, Airy gave his views by studying the wooden blocks, how they float in water, or by studying the ice blocks, how they float in water. So this is Airy's hypothesis. So there is no definite level in the substratum as per Airy, where higher blocks and smaller blocks of the crust are balanced, but the depth covered by the biggest crustal block represents the level of compensation at which all crustal blocks are balanced. So all the crustal blocks A, B, C, D, E, F, they have the same density 2.7, 2.7, 2.7, 2.7, 2.7, but because this is a bigger block, that sinks to bigger depth. Smaller block, smaller depth. Very smaller block, very small depth. So the substratum, it has no definite level of compensation as per the Airy's hypothesis. Here all crustal blocks are of the same density, but they have gone to different depths in substratum due to different sizes of the block. This is Airy's hypothesis. Now let us come to Pratt's hypothesis. According to Pratt, the crustal blocks show different density. Different crustal blocks have different density. They are all balanced at the particular level, that is level of compensation, which is called as the asthenosphere. Denser blocks are smaller in height. Lighter blocks are, and the mountains are higher in height. But all of them are balanced at the one level, that is the level of compensation, which is the level of the asthenosphere. Hence, the weight of the different crustal blocks from their upper surface to the level of compensation must be same. Oceanic crust has higher density, so are smaller in height. Continents have lower density, so they have higher height. So this is continental, this is the hill mass, mountain, less density, so it has gone to greater height. Density increases, height decreases. Density increases, height decreases. Density increases, height decreases. And they are all balanced over one level, which is the level of compensation, and is equal to the level of the asthenosphere below the lithosphere. So according to Pratt, all blocks have different density. They stand at common level. Higher density is represented by blocks of smaller height and vice versa. These are the facts of Pratt's hypothesis. So there is a level of compensation over which crustal blocks of different density stand. And mathematically it can be proved. The density is found to be different, and the pressure at this level of compensation, this is asthenosphere, the pressure is found out for this block, for this block, for this block, for this block. They are found out by these T formula following the pressure as H rho G, density, value of gravity and height. As densities vary, their height varies. Higher the density, smaller the height, and they are found to have equal pressure over the substratum, over the level of compensation. That's why they are all balanced according to Pratt. So this is the formula that has been derived from this. That has been derived. So G rho and the height. G rho height. So this is rho h given by this formula here. Rho z here, rho z below the oceans, that is given by this formula. So this can be easily found out. Let me find one. So here we have the pressure, that is Tp the height into rho c into G plus, as it is the common level, here it is the common level, let us discard it. So this is equal to this T P plus H, this is the height, into rho H into G. So G cancels, and we have this is equal to Tp rho H plus Tp rho H. So rho H, rho H given by Tp into rho C by Tp plus H. So this is the formula, or this is the formula that we get for rho H. This rho H given by Tp into rho C divided by Tp plus this height. Similarly, this formula, this can be compared between these two blocks, so that we can get rho Z, the density of the rock mass below the oceans we get. So according to Pratt, the crustal blocks are of different density. They are balanced over the substratum at one level, that is called isostasy, and the height of the cluster block is controlled by the density. Lower the density, higher the density, smaller the height. This is the view of Pratt. Then let us discuss Hayes-Cannon's hypothesis. Hayes-Cannon's hypothesis. It combines Airy's hypothesis and Pratt's hypothesis. According to this hypothesis, there are crustal blocks which differ in their density. Continental crust is lighter than oceanic crust. Lighter crust appears as raised features, whereas the denser oceanic crust appears as depressed basins. All these blocks do not have a common level of compensation as proposed by Pratt. Here they go to different level. Higher the density, smaller the depth, it penetrates. Lighter the density, higher is its height, and also it goes to a deeper depth. That's why Himalayas present a height of 9 kilometers above ground. It has its root which is about 80 kilometers thick. But there is no ocean basin which is of this much thickness. Hence, thickness and height of different cluster blocks vary. They have penetrated into the different depths based on their density. They do not have a common level of compensation. Again, in each block there is variation of density. As the pressure increases, the density is 2 point here. As you go down, it becomes more dense. It becomes 2.9 or more than that. If it is 3, as the pressure is there, with depth the density increases. So within the same block, we find there is variation in density, and they go to different depth. Lower the density, higher is the height, and higher is its root. So this is the Hayes-Cannon's view. It actually proves the observed facts, because different blocks have different density. We cannot expect that the density of the continental crust and that of the oceanic crust to be same. So crust presents different blocks having different density. Higher blocks have a lower density. There is no common level of compensation. Density varies in a block. Density is more in every block at its bottom. This is Hayes-Cannon's view, which is true as per the observations made over the standing blocks of the earth crust. Let us discuss how the isostatic balance of the crustal blocks are found to be upset. All crustal blocks are in perfect balance. This balance is upset by several factors such as igneous intrusion, sedimentation, erosion, melting of ice sheets from the top of the mountains, formation of thick ice cover where the thickness increases. So, the nature by natural process balances this imbalance in distribution of Earth's material. This balancing is called compensation. For example, from the top of the mountains, the sediments are eroded away by the agents of denudation. They are brought to the bottom of the mountains. So mountains become lighter by this process because of transfer of the earth material from the top of the mountains, or also because of the melting of ice cover that covers the top of the mountains. So this causes the lessening of the pressure over the mountains. The sediments are carried to the basins from the top of the mountains. So basins become heavier. There is sinking of the basins. So at one side there is transfer of material from the highland to the lowland. So because of the transfer of material it becomes light, it becomes heavy. So pressure is more, pressure is less. So it will go rise, it will rise, it will sink. In this manner the balance is being maintained. So basins become heavier, there is sinking of the basins, the materials from the basin must be transferred through depth to the root of the mountain so that rise of the mountain can be possible. In this way equilibrium is maintained and nature makes this balance. And we have seen the isostatic rise and fall. We have the epiorogenic movements. This includes the vertical rise and sinking of the crustal blocks. We see the parts of Norway, Sweden which were covered by Pleistocene ice sheets are now rising due to melting of ice. Similarly, the Himalayas are still rising. They have not achieved complete isostasy. That's why they are rising. Raised beaches in some of the coasts. The sea beach is found to rise. Sagging of the continents due to ice cover. So these are some of the evidences of isostasy. That means balance is being maintained by natural process. So let us come to the conclusion. Isostasy explains the tendency of earth crust to attain equilibrium through natural process by transfer of earth material from one place of the earth to the other. Arthur Holmes and D. Holmes, they explained isostasy by taking into account 4 columns of rock, 4 kilometers high plateau, 1 kilometer high plateau, plain at sea level, and ocean basin of 5 kilometer deep. In all these cases, they have found out the pressure. Pressure is found to be uniform at certain depth below the surface of the earth, and they calculated their pressure up to the depth of 50 kilometers. They found that the pressure of each column at 50 kilometer depth is found to be same. This depth is isopestic level or level of equal pressure. Let us see how mathematically it can be shown. The same formula, the H rho G pressure. So this is a case of the column 1, which is 4 kilometer thick plateau. And the calculation is being made up to a depth of 50 kilometers. So this crustal block, so it is the most discontinuity, 50 generally, it is the most discontinuity. So isopestic level can use at a uniform pressure, level of uniform pressure, which is generally considered to be the asthenosphere. So most discontinuity M assumed to be at a depth of 50 kilometers. So up to 50 kilometers, what is the pressure? Let us find out. In column 1, 4 kilometer thick plateau. So total height of the plateau plus the depth is 54 kilometers. Density, average density of earth is 2.8. So pressure is 54, that is the height, into 2.8 into G. As G is common, we have not taken G into account. So height into density, it becomes 151.2. Similarly, in column number 2, if we take into account 1 kilometer thick plateau and 50 kilometers depth below the plateau, 1 kilometer high plateau. So it is found that total height is 50 plus 1, 51 kilometers. Out of it, the crust is of 36 kilometers, having density 2.8, and mantle is having 15 kilometers thickness. The mantle is having density 3.3. So 36 kilometers into 2.8 plus 15 kilometers into 3.3, it gives 150.3, which is nearly equal to 151.2. Similarly, column number 3, here it is plain near the sea level. The upper 30 kilometers is the oceanic crust, and below is the mantle, below the or the denser, it is having density 3.3, and the upper crust is 2.8. 2.8 crust having thickness 30 kilometers, and rest 20 kilometers having thickness, having density 3.3. So in column number 3, 30 kilometers crust, mantle 20 kilometers. So it becomes 30 into 2.8 plus 20 into 3.3, it becomes 150, nearly equal to 151.2. In column number 4, if we calculate, if we see that the ocean exists, ocean is a 5 kilometer deep, and below the ocean we have the density 2.9, and then up to the 50 kilometers depth, the density is about 3.3. So the column 4 gives C 5 kilometers into density 1.003 plus sediment 1 kilometer thick. So below the ocean basins, the sediments are found to be deposited. Let us say it is 1 kilometer thick. So 1 kilometer into 2.4, which is the average density of the loose sediments. Then the basaltic oceanic crust, which is having density 2.9, and it is about 5 kilometers, 2.9 density. Then the mantle. So here it is said that the 3.3 corresponds to the density of the mantle. So this defines the moho. This defines the moho. Moho. Moho is here, and here moho is here. Moho is here. So moho is here. So below moho, the density is 3.3. So it is about 39 kilometers, because 5 kilometer ocean depth, 1 kilometer thickness of sediments, 5 kilometer basaltic crust or oceanic crust. So rest 39 kilometers is left, having density 3.3. If they are added, it gives value 150.75. So these 4 columns having different composition. One is entirely the hill mass, the other is a plateau with smaller height plateau, the third is the plain, fourth is the ocean basins. All these 4 features are found to be balanced over the isoplastic level, that is the asthenosphere. So all crustal blocks are well balanced over the asthenosphere. They vary in the density, they go to different depths below the earth's surface depending upon their density. Lighter the density, higher is the height, greater is the depth up to which the lighter block goes. Denser the material, lower is the height, and to a little depth the said block goes. This is the theory. This is all about the isostasy. So all crustal blocks of the earth surface are well balanced by natural process through transfer of material from one place to another at the lower level below the continental blocks, below the oceanic blocks that lie over the asthenosphere. Compression takes place by adjustment, and they are all found to be well balanced over the isoplastic level, which is the level of asthenosphere. So this is all about the isostasy. Thank you all for your patient hearing.